Welcome back. Welcome back to all of you on our continuing journey of computational process design. And in the last couple of classes, we are looking at sustainability and how you quantify sustainability in design. How do you do sustainable design? And we have done certain analysis based on we have identified what is LCA, what is general sustainability, and now what we are going to do is most of the design requires, so every process design aim to minimize the energy loss. So now we are trying to introduce certain concepts which is actually working based on the energy, which we call it as exergy, which is an available energy, and emergy, both are available energy measure that uses the concept of surroundings and the environment, and we will see how these terms are helpful in quantifying the sustainable metrics, which I think we can use further for process design. So moving ahead, I think our key reference here is reference number 5, Sustainable Engineering Principles are Practiced by Professor Bhavik Bakshi. So most of the contents from this particular lecture would be coming from this particular reference. So now let us move on. So let's recap on what we have done in the last class, or maybe in the couple of classes where we started with the concept of sustainability. We talked about life cycle assessment tool as a methodology for assessing the environmental impact on the products or process from cradle to grave, which is in turn helpful in terms of sustainable decision making. And we have seen how to incorporate uncertainties into the model making. So there are 3 types of uncertainty: parametric uncertainty, scenario uncertainty, and model uncertainty. And parametric uncertainty is typically available, gives rise from the uncertainty related to data availability, measurement accuracies, which can influence the life cycle analysis. And we also looked at different assumptions about system and system boundaries, and we have also looked at what are functional units. Okay. And based on that, we tried and identify scenario uncertainty and how it would affect our analysis. And we also looked at model uncertainty, where the simplicity or the simplifications that one need to bring in to reduce the complexity, that which actually gives rise to the model uncertainty, and which in turn is an issue in terms of predictive accuracy. So then we have looked at some statistical analysis, some sensitivity analysis, and so on and so forth, and how methods, how to identify reliable LCA calculations. Okay, then I think this was basically how we were looking at in this previous classes, how to look at uncertainty, how to handle uncertainty, and what we call it as input-out models, hybrid models, functional units, and so on and so forth. So now we will go one more step ahead and try to, with these definitions and underlying analysis, can we quantify the energy transfer, energy, and specifically the concepts like exergy and emergy, which can helpful to quantify your sustainability metric. So let's look at energy analysis. So energy has high correlation with HDI, which is the Human Development Index. Countries having higher energy consumption or energy per use capita typically would have a higher HDI, which this is essentially, yeah. So the it's a proxy of the proxy metric for the development. So if you have more energy consumption, it would essentially means that you are producing more goods and even services. So this eventually adding to your HDI calculation. And HDI increases with energy up to a certain point, after which the increases in HDI become less pronounced with higher energy per capita. So typically, as I previously mentioned, increasing the energy use per capita correlates with higher HDI up to a point that suggests the importance of balancing the energy consumption for sustainability. So, beyond that, whatever energy you are consuming is not really converting as does not contribute to the human development, and typically it may not be sustainable as well. So, let's try to recall some of the types of energy, or rather the few how do we, which are the terms that we recurringly see when we see when we look at the energy analysis. One is of course the fuel value, which is defined as the amount of heat that can be generated by combusting the fuel. The heat of combustion and or heat value of various fuels measured experimentally can be reported either as a lower heating value or a higher heating value. This is of course the fuel value. And lower heating value is also known as the net heating value or gross calorific value, is the amount of heat released when a fuel is burnt completely, assuming that the water vapor is produced during the combustion is not condensed and the heat of vaporization is not recovered. And the LHV or the low heating value does not include the latent heat of vaporization of the water during the combustion. So, now look at the other concept, which is the high heating value. High heating value is known as the gross heating value, is the amount of heat released when fuel is burned completely and the water vapor is produced during the combustion, which is condensed and the heat of vaporization is recovered. HHC definitely include the latent heat of vaporization of water formed during the combustion. So, now with this we can of course recall the definition of enthalpy, which we typically tend to use. Enthalpy is described as the thermal energy contained in a substance. The change in the enthalpy is given by the equation delta H is equal to mCp delta T, where m is the mass, Cp is the specific heat, and delta is the temperature difference with respect to a reference temperature. So, this is very important. And we all know this. I think many of your thermodynamic courses or basic mass balance courses would have taught you. So, now let us try to build on the top of this. So, now let us evaluate an energy flow in the process. This process could be anything like a heat exchanger that we have learned early, or it could be a, a reactor system that we have learned earlier. So, now try to manage or rather modulate how energy flow in a process can be quantified. So, energy, and eventually we are typically looking for a network of processes rather than a single processes. So, you can have, if it's a process, there would be a feedstock energy, which is like the energy content of the raw material, which typically you represent using EF, and you need to process the feedstock in the process. This is what we call it as energy processing, which is EPR, which is required to convert the feedstock into the desired product. And the product energy EP is the energy content of the final product that is coming out of the process, and of course the waste energy is the energy that is not converted into the product energy and essentially left over as waste. Now let us play around with these uh, four terms and trying to provide a balance across it. The first law of thermodynamics, which of course we can apply, which eventually give is EF plus EPR should be equal to EP plus EW, and energy efficiency is the ratio of the product energy to the total energy input, which is evaluated as EP divided by the summation of EF and EPR, and this efficiency is less than or equal to 1, meaning that the process cannot create more energy that is fed into the system. So, you utilize some energy, you may convert into that into useful work, fine, and depending upon the efficiency of your process, you will start getting your output. But typically the product energy, which should EP or EW or EP should not be greater than the energy that is being fed into the system. So, another concept is EROI, which is typically called as energy return of investment. Energy return of investment is defined as the ratio of energy obtained from the product to the processing energy. So, EROI in this case is EP divided by EPR. So, it is this diagonal is what trying to relate them. So the EROA can be greater. EROA can be greater than or less than 1, depending upon how do we look at it. Depending upon the process yields more energy in the product than it is consumed during processing. So, so that's the way it is. And the next term is net energy and energetic profitability. So net energy, ENET, is defined as the difference between the product energy and the processing energy, which is calculated as ENET, which is equal to EP minus EPR. So EP minus EPR. For a process to be energetically profitable, the energy contained in the products, which is of course EP, must be more than the energy needed to produce the product, which is EPR, meaning EROI must be greater than 1 and ENET must be positive. So this is another concept that we might use in the subsequent slide. Okay, so let's now move on. So let's look at a simple example so that we can compute some of these metrics. A process for mining the coal require 0.5 mj per kilogram of mines of coal. Okay, the fuel value of the coal is 27 mj per kilogram. Determine the energy efficiency, AROE, and net energy for this process. So we know that the feedstock is coal. The feedstock amount is 1 kilogram. Okay, and the feedstock fuel value, which is given as the 27 mg per mg. So now, and it is also given that the process kind of consumes the processing energy is 0.5 mj per kilogram. So if you assume feedstock amount is 1 kilogram, so you have to actually start a basis. So let's assume that it is 1 kilogram as the basis. It is the processing energy in context is 0.5 mj. So let's assume I mean no loss in moving the coal from inside of a mine to the surface. The product will also be 1 kilogram. So whatever you unearth inside the mine and when to come out, it is the same thing. So the product, the value will also be 27 mj. So now if you compute the efficiency, which is of course EP by EF by EPR, which is 27 divided by 27 plus 0.5, which would be just above 98%. And EROI, which is of course defined as the ratio of EP by EPR, which is 27 divided by 0.5. So this number of course is 54. So ENET. So ENET is of course EP minus EPR. So 27 minus 0.5, which will be 27.26.5 mj. So this is, we have just done some of these basic calculations as an example. So let's move further. So how do we analyze the energy using a nice graphical tool which is known as Sankey diagram. So energy analysis of process is important to determine the fuel value and the enthalpy of streams that is entering and leaving to the system. So let's consider a simple example. In a mixer, you have two streams. One is coming at 100 degrees C, having flow rate of 0.5 kilogram per second. The other one is 50 degrees C, which is coming at again at the same 0.5 kilogram per second, and after mixing it is going out as 75 degrees C with of course two flow rates combined, so it would be 1 kilogram per second. So so let's say if you wanted to compute the enthalpy, which is a key component in the energy analysis, you need to actually fix a reference temperature. Or let's assume that 25 degrees C, which is typically a clean ambient, you consider this as a reference. So 0.5, so MCP delta Tc of hot. So M is Cp is of course 100 minus 25 is 37.5, and cold stream it is 0.5 times 1 times 50 minus 25, it will be 12.5. So this is what has been represented here. Under ideal condition, the enthalpy of the output is the summation of the enthalpy of the input stream. So you come, mix and go. So now, so these calculation now we represent here as a nice what you call diagram wherein you see the energy flow under ideal and practical condition you represent. Okay, and in what you are going to do in ideal condition. Okay, the diagram show no energy loss with the width of each stream corresponding to the enthalpy content. So what is approximate enthalpy content? So you see that this is 12.5 and this is 3 times, almost 3 times higher than that. So you see this width is 3 times of that. Okay, so and both of them combines and you form and in the mixer and goes out, right? So this visual representation, which is actually also quantifying how much is the enthalpy of the streams inside and outside. You mix it and go out, and this such diagrammatic representation is called a Sankey diagram. So now look at a case wherein you have more practical relevance. Okay, then you assume that the process of mixing, there is some 20% or 24% of heat loss. So you see that. Okay, so they combine, mix together, and overall due to the mixing you say that there is some loss of energy. So it should have been a nice rectangle here, but you say that there is, it will be shaved off here and goes out at a different, of course at a different temperature, because your heat, there is a heat loss, so of course this final temperature now you can calculate considering that there is this much percentage heat loss. And what I am trying to say, or what we are trying to showcase here, that you can say that in ideal condition this, this blue rectangle, while due to the losses you say that it has been decreased and finally get out. So this is one sort of a representation of the energy analysis. So this analysis you can do it for mixer, you can do it for any process unit, so which is an important way of visualizing the energy calculation. So now let's look at the net energy calculation. So net energy calculations evaluates the balance between the energy, which is of course the fuel value produced by a system, and the energy in terms of the fuel value that is required to create the energy, focusing on the sustainability of the process. So we slowly started to bring in this concept of sustainability in the design calculation. So let's, what the EROI, or the energy return of investment, is a critical measure within net energy analysis, indicating that the efficiency of energy production process by comparing the energy obtained from the energy expended. So you spend certain energy, you get something out of it, and how, whether that EROI is by considering the efficiency is sustainable or what. So let's look at a small example wherein you have a small monetary flow, in the sense that your 0.833 of x1 minus 0.182 of x2 yields f1 0.1667 x1 plus 0.818 x2 gives f2. So these equations, what is the significance of these equations, etc., we have learned in our previous lecture. So now we use that concept. You say that there are two sectors, okay, and they tend to interact each other. x12 is 10, x21 is 20, x11 has a self loop having 5, x22 has a self loop having 10, and there's a value that is coming in, there's this thing, f1 is going out, and you can see there is you can see that there are also external energy, m11 which is like 300 joules here, m12 which is 100 joules here. And what we are interested here, determine the direct and total energy intensities of two sectors. Suppose the sector 2 produces 100 joule per dollar of fuel. Calculate the EROI. All flows except M1 and M2 are in dollars. This of course the energy flow, rest all are in terms of monetary value. So I'm not going to the details of the calculation. So we know how these things can be calculated by means of matrix manipulations. That's what we have learned in our previous classes. So let's go to the direct calculation. Okay, so the direct energy intensities we compute as M11 minus x1, which is of course 10, R2 which is M12 divided by x2, which is 1.82, and total energy intensity requires the calculation of R star, and you have this 10 R1 and R2 divided by this matrix that is coming from your equations. You say that the right side is not x, so this is like a minus a naught itself, right? So you have to compute this inverse of this particular term. So this is the equation in terms of the matrix form, and we compute the inverse of that, and eventually you will get this number. So this is of course R star. So now let's compute the EROI. EROI requires a little bit more step. So determine the EROI of the from the output sector. Let the final demand of the sector 2 is $1, then F1 is equal to 0 and F2 is equal to 1. So you will have to specify the F1 and F2 in this context. Okay, so let's assume that they are, if it is given, you may use the values as given. So let's, in this particular case, let's assume that F1 is equal to 0 and F2 is equal to 1. So we will be able to solve plugging in F1 is equal to 0 and F2 is equal to 1 to get what is the value of x1 and x2 here, and that is what is being shown over here by means of solving the set of linear equations. So x1 is equal to 0.33 and x2 is equal to 1.49. Okay, so now what we have is you have your R, okay, and we do have the corresponding x, right? So you tend to multiply your m1 value is equal to 10 times 0.33 plus 1.82, correct, 1.82 times, okay, 1.49, which is of course what we have obtained, because this is the x2 value, which would eventually translate to 5.95 joules. You may also do an alternative calculation based on R star and F. We have computed already the R star, and we know what is the value of it's of course the vector matrix multiplication. And once we have that, correct, so now this is the total energy required to produce $1 of the final demand from the sector 2, which is the fuel value 100 joule. So now what is the ERO in this context? Of course, you will have to divide 100 joule divided by 5.95, which is equal to 16.81. So this is how you compute the what you call energy return of investment. See, so now we have done an energy analysis. So energy flow is not only is not alone in the sense, right? So energy is just not flow through any system. So to flow energy, you also need to assume that there would be a material flow. So any material flow is associated with an energy flow, or the vice versa. So for instance, energy flow would eventually means that there is a material flow. So now let's try to balance that as well. So material flow analysis is to track the materials flowing in and out of a system by looking at the inputs, outputs, and changes in the stock between the system. So here the idea is to understand the resources as what is feedback, what is products, are we recycling something, okay, is there a waste material coming out of it, and so that we can find opportunities of improvement in terms of course economically and environmentally. So the key aspect is we are looking for methods that are both economical as well as environmental. That's why the entire concept of sustainability come into the picture. Okay, so now look at an example. Okay, you have we are cooking up a cup of dry rice that requires 2 cups of water. When cooking, 40% of the water evaporates, but with a covered pot, most of the water, of course, recycled back. This is like a normal thing that you see when we cooking, which is of course you see all of this. You have feedstock, you have product, and the recycling, and of course something waste, and leading to a net loss value of only 10%. What is the material efficiency of this process? We can of course assume that 1 cup of dry rice weighs 184 gram and 2 cups of water weigh 480 gram. So now let's try to do this calculation. So what would be the water evaporated during process? So it is 480 gram water and 4%, 40% evaporate. So 0.4 times 480 is 192, whatever that number equates. And net loss of water due to evaporation, it says that the net loss is 10%. So 0.1 times 480 is 48 gram, and we have to say, so we have to identify what is the water recycled. So whatever water is not lost is of course recycled back. So it is evaporated and not lost. So it would be the difference between 182 minus 48. 144 grams of course is recycled back. And what is the weight of the cooked rice now? Fine. So you have 480, fine. 480 is the value of the water, and 184 is the dry rice, and out of which the recycled water you will have to the water that is lost due to the evaporation you would have to discount. So it would be the summation of 480 plus 184 minus 48, and you would eventually come up to 416 grams. Now you can eventually calculate the material efficiency. What is useful mass minus total mass. So the weight of the cooked rice of course is what is useful. So for 616 divided by the total mass is of course 616 plus 48. So this would say that we are close to 92.8% is the material efficiency. So energy efficiency and also material efficiency, you can decouple both of them, or material efficiency and energy efficiency you can't decouple. Any flow of material eventually result in energy flow, and vice versa, as I explained. So having done the footing for the basic energy calculation, so now go back and look at what is this concept of exergy. So, let's see, objects have potential energy with respect to their position. This is of course we are talking about general processes. Objects have potential energy with respect to their position. For instance, an elevated object has a potential energy due to gravity. So ability of the system to do work is dependent upon the difference within the system and its surroundings, like battery, depending upon the concentration gradient between the electrodes. So systems have capacity to do work. So what is exergy? Exergy is a maximum work possible from a system as it reaches equilibrium with the surroundings. So for instance, heat engine operates between a heat source at a temperature T. So look at this, it's a heat source at a temperature T and a sink somewhere here, Q to Q naught. And work is typically done by transferring from heat from the source to the sink. The maximum work of course is proportional to the difference between the source and the theoretical sink at absolute zero. Fine. So but realistically sink is not absolute zero, but of course is at a temperature T naught. So the maximum work considering the T naught would be proportional to T minus T naught. And the maximum work efficiency of that engine is the ratio of the actual work to the maximum possible work. So work max of course is proportional to T, and that is the maximum work that you can extract, but your sink is definitely not at absolute zero. So you can only so much of work you can do. So W, the actual work done, is proportional to T minus T naught, and of course we can compute the ratio of that, which we call it as psi max. W by W max is equal to T minus naught, T minus T naught by T. And if you recall the Carnot engine, right? So this is the temperature gradient. You will have to multiply with the heat value. So the maximum useful work from a heat Q is B is equal to Q times T naught by T minus T naught by T. So this is how we compute exergy. So we can also compute exergy also as an expression like this, B, which is H minus H naught minus T naught into S minus S naught. So this expression is very similar to free energy, but the difference between exergy and the free energy type lies in the chosen reference state and the path during the process. So exergy is defined when the reference state is in the environment. Okay, exergy. That's why exergy represents the maximum work potential of a system in comparison with the environmental state. The reference state for the free energy calculation is typically the final state of the chemical reaction or a phase change. What is that? So this is not the case. So this is, so here the reference state is environment itself. One other one is a hypothetical final state, and the path taken involves the constant pressure and temperature. Typically, when you look at, so there are two free energy calculations, right? One is corresponding to what we call it as Gibbs free energy, where we assume that the process follow a path under constant pressure and temperature. And the second is Helmholtz free energy, which wherein the process typically follow a path with constant volume and temperature. So this is the subtle difference between free energy and exergy, correct? So this is the maximum available energy of that system. So which is of course the definition is similar to the free energy, but the make sure, so here the difference is the reference state is always connected to the environment. So let's see the exergy calculation of 2-3 examples. For instance, consider a case wherein a pressure P is applied to a system and you have got the work done, okay, and environment is at a low pressure at P naught after doing the work done. So exergy due to this pressure gradient B, which is equal to integral P dV, and you have to integrate this between P and P naught, and one way we could eventually use the ideal gas law here in RT naught integral of P naught into dP by P, and once you integrate this become nRT naught ln P by P naught, when is the number of the moles of material. So now look at the case wherein you have higher temperature to the lower temperature. The steam is at the higher temperature, you got your work done, and then of course the environment is at the lowest temperature. So exergy due to the temperature gradient, you see that H minus H naught minus T naught into S minus S naught. So you can compute the substitute the expression for H here, which is mCp delta T, which is dt, and here in terms of again you take out your S out of it, mCp T naught into mCp integral of dt minus integral of T naught to T dt by T. So this would result in mCp T minus T naught and mCp T naught into ln T by T naught, where again m is the mass of the material, like n become the mole here, m is the mass here. So now look at the third case. This is like pressure, here it is concentration. Now look at a case where we have pressure, temperature. Now look at a case we have concentration. So your material at the concentration x1, fine, the material at the concentration x2, and eventually environment is the concentration x1 naught and x2 naught. So in this case, X energy, of course the work done would happen due to the concentration gradient, while this is a pressure gradient, this is a temperature gradient, this is a concentration gradient. So in this case, your B, which is the variable for X energy calculation, is computed as nRTL naught ln x by xi naught, where for single component this is the same as the reference variable also, which would be B is equal to minus nRT ln x naught. X naught is the mole fraction of the substance with respect to the reference environment. So these are the three expressions we typically tend to use interconnectedly, or maybe not interconnectedly per se, depending upon the scenario we can choose one of these. Okay, so now let's look at the certain examples. Okay, so determine the chemical energy of a pure oxygen. So the reference state of is the mole fraction of the oxygen is at the atmosphere, which is 0.2034. So so here the appropriate expression is minus RTL and X naught. So you substitute the values and eventually we are going to get R and T and not equal X naught. So this would be the final expression. And look at a case, air stored at the pressure of 10 atmosphere, determine the maximum work that can be done by releasing the air to this atmospheric pressure. So now we have to use the expression that pertaining to the pressure, which is RT naught ln P by P naught. So the P is at 10 atmosphere and releasing this at atmosphere pressure essentially mean that this will be at 1 atmosphere. So R and T is at 25 degrees C and R is appropriately used as the gas constant. So now let's move back and see move one step and let's see how can we calculate the exergy for materials and reactions, which is of interest to us. So if a substance is present as a different compound in the reference state, then the chemistry of converting it to the reference compound needs to be considered. For instance, that to determine the exergy of a compound P that is present in the reference state R, we consider a reaction that relates P to R. So, let us say here the compound P that present in reference state R. So, P moles of P and Q moles of Q reacts to form R moles of R and S moles of S, and PQR as a stoichiometric coefficient or stoichiometric or stoichiometric coefficients. Okay, and the exergies in this context would be RBR plus RBS minus PBP, of course, Q BQ, and here the BRS are the exergy of individual components and this corresponding moles, and GRXN is the Gibbs energy of this reaction. So, now how to calculate? So, let us again take an example, calculate the exergy of a pure ion metal. So, the reference state of ion is, of course, Fe2O3, that is how you typically see iron. So, Fe plus oxygen yields Fe2O3 and it comes with a free energy of the reaction. So, GRXN is equal to Bf2O3 minus 3 by 2 BO2 minus 3 BFE, and you see that Bf2O3 is, of course, it is not Bfe2O3 is equal to 0, which essentially means that Bfe you will be able to compute it based on the this particular expression. So, this is in connection with materials and reaction. Now, look at a larger case where we have exergy flows of systems. So, in this context, we consider a system, okay, and you have a heat source and a heat sink. Q1 is coming in, Q2 is going out, and you have some, of course, work is being given, work is being extracted, okay. There are components coming in, when heat is being lost out, and so on and so forth. So, it's a general process condition wherein you have almost all such scenarios accounted. So, again, so by the law of conservation of energy, it is very clear that M times H in and Q in plus W in will be equal to M times H out, Q out, and W dot out. So, the dot indicates that it is a rate. So, that is why it means. So, again, so this is the law of conservation of energy, and what is the loss? Exergy loss here, okay. So, M times B in, fine. So, you say that there is no B here, this is simply the conservation of energy. So, if you want to compute the exergy here, okay, M times B in, Q in times 1 minus T by T naught if it is some if there are work done, okay, and Wi in, and you go the MB naught out and Q out into 1 minus T by T naught, 1 minus T naught by T, and W. Also, we now include everything, including the work that is done. And what is SLW is the work lost, and B is the exergy of the material. B is the exergy of the material stream. The loss related to the entropy generation, of course, LW which is equal to T naught into S generated, and this calculation, okay, is called as Gauss-Totula theorem or Gauss-Totula expression. And in an ideal reversible process, you say that there is no loss of work. So, you say your left hand side would be eventually equal to right hand side, but that is not the case in true process. So, eventually you would end up in having certain losses. So, now let us again try to do an example for calculation. So, simple example again, you have two streams coming in having temperatures 100 degree, 50 degree with 0.5 and 0.5 kilogram per second flow, and after the mixing the temperature becomes 75 degree and 1 kilogram per second is the flow rate out. So, what we are interested in calculating the lost work for the given mixing process. So, again B hot would be equal to, so we need to have a reference temperature is 25 degrees C, a specific heat of water is 1 kilogram 1 kilocalorie per kilogram centigrade. B hot is equal to 1 times 373 minus 298, fine, minus of course 1 times 298 ln to 373 minus 373 by 298, right. So, B cold of course is the same thing, 1 times 323 minus 298 minus 1 times 298 ln 323 by 298, and B mixed. So, 75 degree, fine. So, 1 times 348 minus 298 minus 1 times 298 into ln 348 divided by 298. So, and you get 3 expressions. And now so those only the B values, right. So, if you look at the previous expression, it is just not the B, you also have to get multiplied with the corresponding flow rate. So, and some of them are inlet flow rate and some of them are outlet flow rate. So, the actual value would be 0.5 times 810, 0.5 times 0.9 minus 1 times 3.78. So, this would be the lowest work, which would be now computed as 0.77 calorie per second. Fine, if you wanted to compute Sgen, you also have to divide it by T naught, because loss work is equal to T naught times Sgen. So, T naught being 25 degrees C, which is 298 Kelvin, you just we may be able to compute that as well. So, this is how we do the overall exergy balance across. So, how do we improve these measures? So, what is the way to improve some of these measures? Again, we have the Sankey diagram of the mixing process, wherein and so and we see that in ideal condition, this is a nice Sankey diagram. So, 100 degree C your feed in, and 50 degree C your feed 2 comes in, and it goes out at 75 degree C without almost loss. So, now this is the case where you assume that there is a loss of 24% loss. So, now how to improve this a little bit is what we need to look for. So, how do we, so this would be eventually result into something known as Grassmann diagram. Okay, so among the solutions to address the challenge of depleting resources and environmental pollution, the most common suggestion is to improve the technological efficiency. There is no question about it. The more efficient is your process, the lesser would be if emissions, and you shall be able to extract most of the work out of it. The enhanced technological efficiency result in less resource use and reduced pollution per unit of the output. So, Exergy can identify this limit of efficiency. So, now consider the case, calculate the Exergy efficiencies of the given ideal and non-ideal mixing systems. Okay. So this is this is the case. So, let us assume that our mixing is ideal. So, we have 378. So, let us move one step back. So, we have 3.78 B mix, 0.99 B cold, and 8.10 B hot. So, in the ideal mixing case, it will be 3.78 divided by 0.5 times 810 and 0.9. This would be like 83%, which is a good thing. But at the moment you have non-ideal mixing, you would see that this would be reduced by at least 30%. So, 50 to 80, and what we are interested in recovering this full, so that we shall be able to have a better what you call B by H basically. So, this is the B by H calculation. So, in this case you can see, so the input here is B by H, right. So, H is 3.37.5 kilocalorie, B is 4, it's of course on the higher side. Okay, B by H is 0.11, here the B by H is 0.04, here of course the B by H you will have to have 0.08, which is of course which is higher than the one of the input flow rate. This is typically we can attain by means of energy, so improvising the efficiency. So, now let us look at what we call the concept of cumulative exergy. So, cumulative exergy consumption is a holistic measure of exergy used both directly and indirectly in a process or product's life cycle. It is analogous to the life cycle energy consumption or energy, what we call it as the energy footprint. So we have materials, we have computed material footprints last time. So this is like energy footprints, and CEC is kind of an aggregate measure that aggregates the exergy from various resources like renewables, non-renewables, materials, water, assessing their capacity to do work. And how do we compare this with other footprints? So similar to the footprints analysis that we have done for water, so CEC provide a broader view compared to the carbon and water uh, footprints. So carbon footprints accounts only for the greenhouse gases, while the water foot only account for the water. But now we are talking about cumulative exergy consumption, which is a broader paradigm. So you're not only talking about fuel, not only talking about water, of course, a holistic mix of everything. So CEC considers the full spectrum of physical flows, making it a comprehensive term for sustainability analysis. So exergy efficiency of a life cycle. So this is typically defined as the ratio of exergy content to the product of the cumulative energy consumed to create that product. The ratio is known as cumulative degree of perfection, which is also called as CDP. We have certain some more details are coming in at a later slides, which measures the exergy efficiency of a life cycle. So cumulative degree of perfection is that particular um, uh, metric that helps you to measure the exergy efficiency of the entire life cycle. So how do we do this mathematically formulate? So the exergy efficiency psi c of a life cycle is given by B by C, where the cumulative energy exergy consumed C is the sum of the exergies of the natural resources, which is of course sigma Kn times Bkn used directly in industrial processes. If the industrial inputs are not directly obtained and involve intermediate processing like mining or manufacturing, CEC is the sum of the exergy related to each input. So some of the industrial inputs are now directly coming in. So your raw material will have multiple sub-steps of conversion until it becomes the real feedstock. You will have to. So exergy is the sum of the exergy of each such inputs. So CK. So now look at two small examples. So you have two process. One is kind of converting coal to electricity. So you what you do, you have coal, you have to extract the coal, and that for which you have to spend in some energy, and it goes to the furnace, and furnace you will have to again supply energy, and it would become steam and steam turbine, and of course there would be exhaust gases from the furnace, and steam turbines produce electricity, and you have to finally you condense the steam and you compress the steam that would of course fed back for the process to continue. And look at the other case wherein you have solar radiation, so which is this is a purely a non-renewable cycle, and look at this renewable cycle wherein you have a solar radiation which is collected through parabolic troughs, and you kind of that you send into heat exchanger. Fine. So solar radiation is coming in and you are collecting through trough, and this would of course result in some sort of steam generation, you can see, and this would work in steam turbines and of course condensate compressor, and the process is repeated. So now what are we interested? So determine the degree of perfection. So we have defined the degrees of perfection previously of the furnace and the coal extraction process, and the cumulative degree of perfection of the coal based electricity life cycle, which is this route. And of course for the process B, determine the cumulative degree of perfection of solar thermal power generation, which is over here. So now let's look at the case here. So the energy of the input rate of energy input rate of the coal is 141.95 kilowatt. Required fuel oil is 705 kilowatt, and of course electricity generators 34.51 kilowatt. So degree of perfection here would be okay. So 34.51 divided by 141.95, which is 24.3. Okay, and this degree of perfection of the extraction become 141.95 divided by 141.95 plus 7.05. And what is the cumulative degree of perfection, which is of course 34.51 divided by 141.95. 95 plus 7.05. So this is for the non-renewable cycle. Now let's look at the renewable cycle. So energy input from the solar is 270.82, the electricity generator is 34.51, and here the calculation is fairly straightforward. So input rate, the cumulative degree of perfection is of course the ratio of this versus this is like 12%. What you can see here, here the cumulative degree of perfection is what you call low as anticipated. This is because the smaller solar process. So the because the process is highly dependent upon the dilute nature of the sun. Dilute nature of the sunlight or seasonality compared to coal, which is a definite energy resource. So now let's compare. So we have now two resources we have seen, right? Similarly, how to now compare across resources. So here there is one of the resources were coal, other one was sunlight. So how do we do this analysis across resources? So the next is that about resource quality comparison. So the quality of the resource such as food and fuel can't be determined solely by their energy content, because look at twinkle and bananas, they have the same calorific content, but they are not considered to be substitute because of the different nutritional value and content like fat and essential nutrients. So there is some way to do this calculation. One is of course convert everything to million per gallon equivalents, which is MPG. So million per gallon equivalent is a measure that is used by Environmental Protection Agency to compare the fuel efficiency of different types of vehicles, including electric cars and hybrid cars. So it equates how do we compute the miles per gallon equivalent? It equates the energy used by the electric vehicle to the amount of gasoline that would provide the same energy, thereby allowing the comparison of different fuels. So for instance, so let's look at certain calculations. So compute the MPG equivalent of plug-in hybrid electric vehicle that travels 20 miles on gasoline and 50 miles on battery power. The efficiency of each engine is 50 mpj for gasoline and 30 kilowatt hour per 100 miles for electric. And of course, the conversion factor is 1 gallon of gasoline contains 115,000 of BTU. So now let's look at how to compute it. The total distance traveled is 70 miles. Energy obtained from the gasoline for 20 miles at 50 mpg would be 20 by 50, okay, times multiplied by 115,000, which is like 46,000 BTU. And the energy from electricity for 50 miles at 30 kilowatt hour per 100 miles would be 30 by 100 times 50, and this conversion factor from kilowatt hour to BTU, which is 3412. And what is the total energy, which is of course the summation of both, okay? Total energy for 75 miles would be summation of this, and MPG equivalent is the total miles driven times energy 1 gallon of gasoline and the total energy of all fuel consumed to cover the distance. So total miles driven is 70, energy of 1 gallon of gasoline is of course 115,000, and total energy of all fuels consumed to cover distance. So this would be equivalent to 82.84 mpg equivalent. So now we coming to the concluding part of this class. So what is emergy? So this is the third topic that is in the title. We talked about energy, we talked about exergy, and what is emergy. So let's understand what is this concept of emergy. All of them would be useful in sustainable design. So emergy is the total energy, of course, used in both of its total energy as in exergy. Okay, of course we are only considering the exergy, not the free energy, used both directly and indirectly to make the product of a surface. So this is so we are now, so in exergy we typically use only direct contributions. So here we also consider the indirect contribution. So making this as the one of the wholesome analysis, correct? Wholesome metric that is helpful to analyze. So it includes the direct and indirect flows of available energy representing all resources in terms of solar equivalent joules. So, SEJ is the typical um, what you call unit that you want to represent it. Why you need to do such an equivalent? Why? Because you have indirect measures. So, you need to considering that sun powers everything. Okay, so you will have to, so the simplest or rather the so it is fair to represent the total uh, each of these components energy as a solar joule equivalent. So, energy captures the energy consumed in ecological processes, not just industrial ones, which is termed as ecologically cumulative energy consumption. That is what it means. And you also need to know what is this transformity factor. So, transformity is defined as the ratio of energy to the exergy given as tau. So, this would now say that how much would be so this is like an indirect measure, okay, uh, of which you can also include the effect of indirect components which is present in the service. So, again the unit here is solar joule equivalent, okay, solar joule per joule, because you have exergy you typically represent it as joule. So, SEJ divided by J is the SEJ per J is the typical metric or unit that you would like to represent transformity, which allows the comparison of the quality of different energy forms. So, higher transformity indicates that higher energy quality, suggesting that more energy was used to make more energy was used to make the product. So you use the contribution from direct contribution and indirect contribution, and uh, it is the best, right? So you are not missing anything. So this is, so energy is the I would say the wholesome metric that kind of connects both direct and indirect contribution of exergy that is gone inside making a product or service. So let's again take the same example. So calculate the solar transformative for both the processes. The transformative values of coal is 40,000 SEJ per J, fuel oil 50,000 SEJ per J, sunlight of course it is a sunlight equivalent, so 1 SEJ per J. So now look at what are the factors. Okay, so so tau A in this case is 141.95. You have to multiply that with 40,000, and fuel oil comes 7.05. You will have to multiply 54,000 divided by the exergy value that we have just computed, which is right here. So the value that you have already computed, which is 334.51, which is the electricity generated value. So when you compute the ratio of that, what we are going to get is the transformative factor, which is tau, which is the ratio of m by b. So now let's move on. You can, so we will leave this as an exercise for you to do. Okay, so you can also compute it for tau b. Okay, wherein your 270 and 34, because there is no intermediate steps, there is no fuel oil coming in. Okay, solar radiation of course has a CJ value of 1. So now how do we do the algebra of energy? Okay, so we have done exergy algebra. So if you recall, what was the exergy algebra? Exergy algebra was about this. This was how do we do the exergy algebra or balance of exergy across systems. Similarly, we now are not going to do the algebra of energy. So that kind of completes the analysis. So allocation in energy accounts for the quality and origin of energy input, allowing a consistent assessment of sustainability. Unique to energy analysis, allocation methods handles splits and co-products differently to maintain relevance and accuracy in the face of incomplete information. Splits occur when the products can be produced independently. The allocation approach distribute the energy potential to a property of the product such as their energy or exergy. Co-products are produced together or which are cannot be separated. So the transformative factor of core products are the same. This is some of the ideas that we consider while using the emergy calculations across boundaries. For split, the emergy values are allocated separately. Renewable resources allocated as co-products, while the renewable resources are treated as splits. So now look at how do we compute the energy of a product. So there are three summation terms. So in first case, you take max across tau I BRI. Fine. So what is BR is the R stands for the renewable. So for the renewable case which are obtained at the same time period, you take the maximum out of it. And what is RT here? RT is the is for the renewable that is coming from different time period, so which is older one. So you take the sum out of it. And in the third term has n subscript n, which is talking about the non-renewable. So this summation of all these three things together would give you the energy of a product, which is product M. So now let's look at take a calculation of here. So for instance, determine the energy and transformativity of 500 joules of a product that consumes 100 liters of rainwater, 1000 liters of rainwater, 2000 liters of groundwater, 50,000 joules of sunlight, 15 liters of diesel fuel. The fuel value and density of diesel are 43.1 mJ per L and 0.832 kilojoule per liter respectively. The exergy of water is 0.75 kilojoule per mole. And the unit energy values of rainwater, groundwater, diesel and sunlight are are these numbers respectively: 30,600, 3,98,000, 1,81,000, and of course for sunlight it is 1 respectively. So how do we compute for? So we need to of course convert this 0.75 to corresponding kilojoule per liter. So this transformation is just to make sure that 0.75 is converted into kilojoule per liter. So it is kilojoule per mole, and you are now coming to kilojoule per liter. So now look at the calculation. So rainwater and sunlight are renewables that solely depend of solar exergy at the same period. So you only need to compute the maximum of one of those. So 50,000 is the sunlight times 1, okay, 1000 times liter of rainwater, okay, and this is the conversion factor times the exergy of water. Now the other two, the groundwater uses exergy mainly from the previous year. Why? Because you have to recharge the groundwater, but rainwater is immediate, so there is no time loss in that context. Fine. So in that case, what you have to do? You have to do the summation. Fine. So diesel rely on ancient solar energy because it is digged under the earth, which was certain. So these, because these materials were embedded inside the earth, and over a period of time they became the fuel. So diesel, so it's an old resource. So it's, and also it is non-renewable. So in this context, what you have to do is, so of course for the groundwater 2000 and the conversion factor and the corresponding exergy, and for fuel for a diesel again 15, and you will have to use this further conversion. So the fuel value and the density of the diesel is already given, so you'll have to multiply that and also corresponding MRP, and when you sum it across you will get the value of M, right? And if you are interested in computing the uh, the the factor transformity, okay, so it is M of course divided by the total number of product that's being used. So it is, you have to divide that by 500, and this is what we are going to get. So we have now looked at the these metrics individually. So now let's try to aggregate them together. So can we have one single metric? So you have looked at exergy, we have looked at energy, we have looked at normal energy. So now can we just aggregate them together and just make single metric? Okay, so some of the single metrics that you can use are renewability index. Ri is the ratio of the energy from the renewable resources to the total energy of all resources. Okay, so My is of course the summation of Mf, Mn and Mr. Okay, so Mr is the renewable, Mn is the non-renewable. Okay, and appropriately we compute it. And higher Ri is preferred for sustainability as it indicates the greater proportion of renewable resources. The next is energy yield ratio. So EYR measures the ratio of energy of the product to the energy required to make that product, which is My by Mf. Okay, it is similar to the concept of energy return of investment, but cannot be less than unity in this case. The higher EYR suggests a more sustainable process, which essentially means that more energy output per unit of energy is given as input. And the next is environmental loading ratio, ELR. It is the ratio of the non-renewable energy and input from the economy to the renewable energy. So it is Mn plus Mf by Mr. Okay, it indicates the environmental impact of non-renewables and non-local sources. Lower ELR is the better. And the last is sustainability index, which is the ratio of EYR, which we have computed here, and ELR, which is we have computed here. So this is a single metric that kind of takes care of everything. So larger the value of sustainability index indicates that we are talking about a process that is highly sustainable, combining various aspects of high yield and low environmental load and so on and so forth. So when we design any process, we would like to have its sustainability index to be as high as possible, renewable energy index has to be as high as possible, and energy yield ratio and environmental loading ratio should be accordingly set. Okay, so I think we are now concluding our discussion today. We will just summarize what we have learned. So energy, what is energy analysis? It evaluates the quantity of the energy in various forms consumed and transformed in a process aiming to increase the efficiency and energy losses. Exergy analysis assesses the useful energy within the system that can perform to work, considering the quality of energy and its potential to cause a change, but relative to the environment as environmental state. And transformity is a measure of the energy quality by indicating the amount of solar energy required to generate 1 unit of energy, with high value signifying the great energy transformation and good quality. And energy analysis is account for the total energy that combines both direct and indirect to produce goods and services standardized to solar energy, providing a comprehensive review of environmental impacts and sustainability. And there are various sustainability metrics, for instance, renewability index, energy yield ratio, and environmental loading ratio, and sustainability index to assess the ecological and economic sustainability of the process. And there are other metrics, for instance, exergy efficiency and cumulative exergy consumption, which offers insights into the performance and environment viability of technologies and process, considering both renewable and non-renewable resources. And ideally, we would like to have our design to be meeting or maybe giving the best metric values in each of this. So we will try to look into that aspect in the upcoming class, wherein some of these issues we would try to take up. And with this, we will conclude this lecture and see you again in the next class. Bye.